Thank you for the invitation. It's my pleasure to present today on some research I've been doing over the last three and a half years. It's on the quantum simulation of gauge theories, as you see in the title. And this is a field that has gained a lot of traction recently. And I would like to present on some subset of the research we've been doing, first in Heidelberg, then Trento, and now here in Munich. So the major goal that we are trying to tackle is probing far from equilibrium gauge theory dynamics. But why do we care about this? Well, there are two main relevance points that I will outline for you. The first one is when it comes to high energy physics. So gauge theories are fundamental frameworks of modern physics, and they are actually the staple of the standard model. So as an example, you know of quantum electrodynamics, or QED. That's the gauge theory describing the interaction between light and matter. Another gauge theory is QCD, or quantum chromodynamics, which is the gauge theory describing the strong interaction between quarks as mediated by gluons. And these gauge theories are studied in dedicated particle colliders. You know of CERN, the Large Hadron Collider, or as in this photo, the relativistic heavy ion collider. And these wonders of science and technology give us a lot of data into the inner workings of nature, but we need to analyze this data. In fact, nature has a lot of processes that involves strongly coupled matter at high densities and far from equilibrium that classical computers are not able to handle so well because of entanglement buildup. As an example, let us consider hadronization. We collide heavy ions at such high energies that they disintegrate into their fundamental constituents, which are quarks and gluons. But then data from these particle colliders show us that these quarks end up binding and forming hadrons, color neutral hadrons. But the strong interaction cross-section occurring here involves a lot of non-perturbative, out of equilibrium dynamics with a lot of entanglement buildup that is really tough to handle on a classical computer. So what people do is they test various phenomenological models with various degrees of approximation on classical computers, but these cannot give us a first principles understanding of what's going on here. So we ask the following question: can we find a complementary venue that allows us temporal snapshots of the dynamics occurring here? Furthermore, can we find a complementary venue that affords us tunability, where we can test different theories that describe this dynamics here from a first principles approach? The other point of strong relevance is in quantum many-body physics. In particular, the fundamental question of how do isolated, interacting quantum many-body models equilibrate? So we know that during unitary time evolution, subsystems of a quantum model get entangled with each other, and so now we can talk about thermalization through the lens of entanglement entropy. We know that in certain cases, subsystems do thermalize, in other cases they don't, and even at infinite times, they exhibit exotic, non-thermalizing dynamics. Currently, we deal with understanding this fundamental question through classical methods on classical computers, such as tensor networks, and these are mostly limited to one-dimensional or quasi-one-dimensional systems due to entanglement buildup. So again, we ask the same question: would we be able to find a complementary venue that affords us quantum advantage so that we can handle entanglement entropy naturally, and so that we can go to higher dimensions and longer evolution times, which will really provide us deep insights into the question of the equilibration of isolated many-body models? Furthermore, would such a setup allow us to control and extract this exotic non-thermalizing dynamics to leverage for technological applications such as quantum metrology or quantum error correction? Our approach to tackling these questions is through the large-scale quantum simulation of gauge theories. We basically hark back to the wise words of Richard Feynman from 1982, who said that nature isn't classical, it's fundamentally quantum, and so if you want to model it, we better do so on quantum mechanical devices. And this ushered in the age of quantum computing, or more technically, quantum simulators, And these are nothing but tabletop, accessible, tunable quantum hardware that we are able to realize in the lab to probe the nature or the realities of nature. And here I show you a photo of such a setup in the Bloch division in Garching with a very motivated postdoc looking on in the background. To put things on a bit of a more formal footing, and I will try not to be so technical in this talk, let us consider the paradigmatic Schwinger model, which is nothing but QED on a one-dimensional discretized lattice. As you can see, it is composed of matter sites that can either be empty or occupied with negatively or positively charged matter. There are links between these sites on which electric fields live. Let us call the Hamiltonian driving the dynamics of the system as H0. Now, a fundamental property of every gauge theory is the so-called gauge symmetry, which here is embodied through this locally conserved operator or generator, Gj. Technically, it generates the U1 gauge symmetry of this model, but basically, conceptually, all you need to understand is that it stipulates an intrinsic local relationship between matter occupation on this site and the allowed configurations of the electric fields on neighboring links. That's it. Basically, it's nothing but a discretized version of Gauss's law that we know and love from electrodynamics. And now what we want to do is map this gauge theory onto a quantum simulator that we can go build in the lab and use to probe the physics of this gauge theory. In nature, this electric field is infinitely dimensioned locally. It has infinitely many local degrees of freedom. And so we take a baby first step towards experimental feasibility by modeling it as a spin 1/2 system, a two-level representation. This is a so-called quantum link model. And even though it's a crude approximation, it still captures a lot of interesting physics, as I will show you. And so we do a perturbative mapping of this quantum link model onto a Bose-Hubbard lattice. Basically, this is an optical lattice quantum simulator where ultra-cold bosons live. And I introduce a staggering potential that differentiates between deep lattice sites that represent the links of the gauge theory and shallow matter sites that represent the matter sites of the gauge theory. I further introduce a constraint allowing only 0 and 2 bosons on these deep lattice sites, which represents the two polarizations of the spin that are allowed here, which represents the electric field. So think of the electric field as simply the Pauli matrix, sigma z or SZ. And on matter sites, I have a constraint of either 0 or 1 boson, which represents the presence, the absence or the presence of matter, respectively. Alas, we find out that this perturbative mapping captures at leading order this gauge theory that I want, but there are unavoidable errors, lambda h1, which will explicitly break the conservation of this generator Gj. And this is a major problem that plagued initial attempts at gauge theory simulators and restricted them to mere building blocks of a single site and a link, where obviously obtaining non-trivial physics is quite difficult. And so we solved this problem by introducing the concept of linear gauge protection. Basically, the upshot is introducing this linear weighted term in the generators Gj, which are experimentally very feasible and require less engineering overhead than implementing the gauge theory itself on the quantum simulator, which makes our experimentalist colleagues very happy. And now by tailoring these coefficients Cj in a smart way, you are able to properly energetically isolate the gauge theory sector on your quantum simulator from other sectors that pollute its physics. Technically, this is based on the quantum xenodynamics, but the whole point is just you make an island out of the sector where the gauge theory occurs. You just energetically separate it from all other sectors on the quantum simulator. And this leads then to a beautiful two-regime picture. One of an uncontrolled violation regime when this error is vanishing, when this, protection term is vanishing. And then you cannot make a formal connection to your gauge theory. You get a soup in your quantum simulator that does not really represent faithfully a gauge theory that you are interested in. And a second controlled violation regime in the presence of this term that gives us a well-defined quantifiable error on the quantum simulator that we can tune and suppress up to all experimentally relevant times, which gives rise to a reliable quantum simulator of large-scale gauge theories that allows us to probe interesting physics in the lab. So the analytical and numerical details behind this work are in this PRL and in this PRX quantum. Good, so now let's do some interesting physics on this platform. We first looked at the Coulomb phase transition that takes us from a phase where matter occupies each and every matter site to a phase where every matter site is empty. This is a quantum phase transition based on the spontaneous breaking of a global Z2 symmetry. We were able to do this on our quantum simulator optical lattice with 71 sites, which was the first large-scale quantum simulator of gauge theories. And then we showed and proved analytically that through introducing a small tilt and tuning the Bose-Hubbard lattice parameters accordingly, we are able to obtain an effective gauge protection term that takes the following explicit form on our quantum simulator, which allowed us to certify for the first time gauge invariance on a quantum simulator, and we measured this violation to be less than 10% throughout the entire duration of the experiment, which is 120 milliseconds, but basically if you want to think in terms of inverse tunneling strength, it is around 6. Good, this work is reported in this Nature article, and then we used this quantum simulator to probe the thermalization of gauge theories, which is a very interesting and open question when it comes to the early universe or heavy ion collisions. Of course, here we do a simple one-dimensional toy model with a two-level representation of the electric field, so we are nowhere close to probing the thermalization of heavy ions, but nevertheless, this is an important and necessary first step towards that holy grail. And here what we did is we start with a Hamiltonian determined by some mass of the quantum link model gauge theory that I outlined earlier. And we quench with it initial states that only have in common the quench energy with respect to this Hamiltonian. And so I show you here an example of two cases where we see that the chiral condensate, or the matter occupation in the lattice, quickly equilibrates into a steady state that we were then able to model using a thermal ensemble with a well-defined temperature. And here I extract the temperatures of these steady states. Details of this work and more experimental data is reported in the Science article. And so now that I showed you thermalization, where again we see a local observable very quickly equilibrating into a steady state, it would be pertinent to try and extract locally the quantum information of the initial state. Not only can I leverage this for insight into the equilibration of isolated many-body systems, but also perhaps I can leverage it for technological purposes. And this ushers in the beautiful exotic dynamics of quantum many-body scarring. Basically, conceptually what happens is the following. I tailor my Hamiltonian in such a way that my initial state is trapped in a cold subspace that does not thermalize. And then you can locally retain information of your initial state, as you can see here in these persistent coherent oscillations throughout the entire duration of the experiment. A bit more technically, what happens is the following. You prepare your initial state with huge overlap with these eigenstates of the quench Hamiltonian. These are the quantum many-body scars that have anomalously low entanglement entropy, rather than being thermalizing like the other eigenstates. And then in theory works that came up later in this PRB letter and PRB editor's suggestion, we showed that quantum many-body scarring has a gauge theoretic origin. And in fact, we went to higher representations of the electric field numerically and analytically, so not experimentally. And we were able to show that scarring persists and is actually quite prominent. So this is really interesting because this is one exotic dynamics relevant to high energy physics that we found, but it's not detected at the LHC or these particle colliders. So this shows that these quantum simulators can be useful in giving us insights not available at the LHC or not yet detected at the LHC. And now let me show you one more example of exotic dynamics, and that is confinement. So confinement is very relevant, not just in condensed matter, but also in high energy physics. In fact, color charge confinement of quarks is the holy grail of QCD. And so here, using our toy model, we take a first step towards that end goal by introducing an extra staggering between these deep optical lattice sites that represent the links of the gauge theory. By doing so, we are able to implement on our quantum simulator the so-called topological theta term, which is relevant to high energy and condensed matter, for example, when it comes to axion electrodynamics. And this term chi, basically, what it does is it enforces an energy penalty on the growth of the electric string between an electron-positron pair. And so pictorially, what we expect to happen is the following. When chi is 0, an electron-positron pair is free to propagate and should propagate ballistically away from each other. While when chi is greater than 0, I have an energy penalty and the electron-positron pair would be expected to be bound up to all times. And in a fresh out of the paper oven that just came out this morning, we show experimentally through a quantum gas microscope, indeed this picture. We start in the vacuum with an electron-positron pair on top of it, and we quench it with the toy model that I explained earlier at different values of chi. Whereas when chi equals 0, we see a ballistic growth of the length of this electric string. As we tune chi to larger values, we see that the electric string remains at its initial value up TRX Quantum, and please check out our archive preprint. Good. So now, what about the future? So I showed you a very simplistic toy model. If you want to be able to be useful to our high energy colleagues, we need to do several things. The first one is we want to go to 2 spatial dimensions on the way to the eventual goal of 3 spatial dimensions. 2 spatial dimensions is also necessary if we want to implement a magnetic field on our quantum simulator, which is not possible in 1D. And so in a recent proposal, we outlined how we can go to 2D scalar QED, or the Abelian-Higgs model, using ultra-cold bosons and a 2-level representation of the electric field. And we benchmarked this using matrix product states between the gauge theory and the Bose-Hubbard quantum simulator onto which we map it. And we see quite good agreement between the gauge theory and the Bose-Hubbard model itself. And you see here that the gauge violation is quite well suppressed and controlled up to all times. We also want to go to higher representations of the electric field. Obviously, 2-level representations are quite simplistic. So we want to scale up the electric field to approach the limit of QED. And this is a well-controlled approach to QED. It asymptotically goes to QED as you model the electric field as a spin S operator and take S to infinity. So there are theoretical works that show this beautifully. But basically, also going from spin 1/2 to spin 1, which we do in this proposal, is enough to give rise to a gauge coupling term, which in the spin 1/2 2-level representation we are not able to do. So here, instead of having only 0 and 2 bosons in the deep optical lattice site, we have 0, 2, and 4 bosons. And as we show in this preprint, this really gives you a 3-level representation of the electric field, which benchmarks nicely if you compare the Bose-Hubbard model that will be the quantum simulator implementing this gauge theory, and if you benchmark it to the gauge theory itself. So here, to note that when you go to spin 1, then you necessitate nearest and second nearest neighbor interactions in this extended Bose-Hubbard model. And we have ideas of how one may be able to do this using dysprosium bosonic atoms. But we also have ideas that we are exploring now where we can integrate out the matter fields and basically end up using only nearest neighbor, end up requiring only nearest neighbor interactions. And now to show you the interesting physics that we see when we go to spin 1 that we could not see in spin 1/2 is a tunable gauge coupling term, where again I prepare on top of my vacuum an electron-positron pair, and I see that when I have a vanishing gauge coupling term, basically the electron-positron pair just propagate away from each other, as you see here in the Bose-Hubbard model mapping of the gauge theory and in the gauge theory itself. But at strong gauge coupling, I have nice confinement up to all times. 5 minutes? Okay, good. So now, all I have shown you is abelian gauge theories, and you may ask me, okay, what are you talking about? I want something non-abelian to go to QCD. And here comes in the following recent proposal that we did, and this is with Fabian and Annabelle and also Lucas and I will discuss these contributions a little bit later. So basically, we propose a two-dimensional SU2, simple SU2 gauge theory. SU2 is the gauge group of the electroweak force. It's non-abelian. What does non-abelian mean? It means instead of having one locally conserved generator, you have multiple non-commuting ones on your local constraint. That's it. And here we propose this honeycomb architecture in the matter sites, which I denote by X. And basically, the circles are so-called Rishon sites. So we don't need to go into technical details, but one link has two such Rishon sites, and these Rishons are fermions that discretize the electric field, much the same way as I discretize the electric field in the abelian case using spin operators. So here we use fermions instead. And now what we do at every vertex, which is composed of a matter site and three such Rishon sites, we make use of the naturally arising dipole-dipole interactions between the ultra-cold molecules that I use to represent the degrees of freedom of matter and the electric field. And by doing a proper Floquet driving, I end up getting Heisenberg interactions between these four guys. And this Heisenberg interaction, I am able to tailor it such that I live in the SU2 subspace, and this will enforce an SU2 gauge symmetry locally. And Lucas Homaya, our PhD student, came up with a brilliant experimental proposal where he basically said, okay, if we arrange the ultra-cold molecules in such a configuration, we lift the one representing matter above the plane, but we have them all at an equal distance. We are able to get this Heisenberg interaction through some Floquet term, which will also induce tunneling between ultra-cold molecules on a link on this large geometry. And now what we are able to do is to locally enforce this SU2 gauge theory. You may be asking, how are you encoding the colors? Well, we have three internal rotational states of these molecules, and basically these will represent the absence of a particle, its presence, and its spin, in case it's present. And now again, to show you the importance of why we need to get quantum simulators of these gauge theories, we are not able to do this in ED or using tensor networks, this geometry. So instead, we demonstrate our findings on the simple geometry where the four circles on the corners are actually matter sites. And we just put one matter particle in this lattice. The other circles are the Rishon sites. And what we do is we quench the system and we see how this matter particle spreads. And I look at the staggered magnetization, occupation, and we see we get really interesting dynamics within experimentally accessible scales. And now we can show analytically and numerically that depending on the strength of the tunneling and the Heisenberg interaction, which we can tune geometrically by the distance between these vertices, we are able to get a controlled violation, just like I showed you in the preliminary slide, that goes as t squared over j squared. T is the tunneling strength, which actually is my gauge breaking term here, and j is my protection strength, if you wish. And so this is really well controlled, and we can formally connect to a gauge theory. And we are able to extract an effective gauge theory Hamiltonian, and its dynamics are the shaded region, which you see reproduce the microscopic dynamics quite well. And if we extract its matrix elements, we see that we have really interesting gauge theory terms, including plaquette terms, particle-antiparticle hopping, and pair hopping as well. So to summarize very quickly, we are seeking a quantum advantage which can naturally handle entanglement buildup. This is general to all quantum simulators. We also want to provide a useful tool to hopefully analyze high energy phenomena, such as how exactly this hadronization happens. This is a holy grail, a really long-term goal, but we believe we are on the way. And finally, in a worst-case scenario, our studies will provide deep insights into the equilibration of isolated many-body systems, because you get these really interesting one-dimensional and two-dimensional systems where you are able to introduce a lot of interesting local constraints, so these gauge symmetries, and then you can tell, okay, if I add this constraint, what happens to my equilibration dynamics? And this is a short-term driving goal. Very finally, I would like to thank my collaborators. This is a large collaborative effort. I've been heavily involved in the group of Fabian Grust, because he pays me, And there are the groups of Philip Hauke, Ian McCulloch, and Zlatko Papic, who are involved in all the results I discussed today. And of course, our experimental colleagues in Shenzhen and Hefei, China. Thank you very much, and I open to your questions.
Okay, thanks for a great talk. Questions? Yeah, Monica.
Oh, sorry. Hey, Chad, thank you so much for this great talk. Really nice results. I have a question about this gauge violation for the 1D mapping, the quantum link model.
Mm-hmm.
Do you actually know, did you check if it does not violate the gauge criterion for longer times, but effectively just implements a different effective model, like maintaining the symmetry? So not that the symmetry breaking terms are a problem, but they just look different compared to the effective model that you were trying to implement.
Exactly. So the gauge symmetry will be exactly the same. It will be U1. We have ways of enhancing the symmetry, which is what we did in the pseudo generator. There you get a richer symmetry when you introduce that same protection term. But here in the example that I showed, you really preserve the local U1 gauge symmetry, and you get a renormalized gauge theory. So your errors will just be renormalized. You will get, instead of getting the Schwinger model itself, you will get some other terms. Whether these terms are relevant or irrelevant from an RG point of view, this is something we are investigating.
Right. Okay, and the last question, why does prosium for the higher spin?
Sorry, why what?
Why does prosium for the higher spin?
Because we need these longer range interactions, like nearest neighbor and next nearest neighbor.
Okay,
so this prosium should be able to avoid this if you do a zigzag geometry.
I see, but you still have the high occupation per site, right?
Yes, exactly,
okay.
Yeah. But we have ways of mitigating this. So I'm gonna surely reduce it to nearest neighbor, not nearest neighbor and next nearest neighbor for sure. About matter occupation, I'm thinking about reducing that too, but let's see, yeah.
Okay, more questions? This corner is very active.
Thanks, Chad, and great results about the confinement-deconfinement transition.
Thanks.
So have you looked or thought about doing this beyond two charges in the system? So like
beyond, sorry, what?
Two meta charges in the system.
Yes, I mean, here we are limited by noise, of course. I mean, at some point, decoherence kills you. And actually, what I did not mention, because due to time limitations, is the quench that we did here is we start on top of the vacuum, and we have, with an electron-positron pair on top of the vacuum, and then we do a large mass quench because we don't want electron-positron pairs to proliferate. We only wanted this electron-positron pair and to probe its confinement and deconfinement. But when it comes to more pairs, we actually have ideas of looking at meson scattering, where we have these two pairs and we are colliding them into each other. The problem is we need much longer times than is experimentally accessible to see their collision, so we're thinking of ways to go about that, yeah. But good question.
Okay, any urgent last? Otherwise, I would propose to approach Jad afterwards and move on to the next session, actually.
I'm here all day, so. Yeah.
Great. And we have a new chair. Who is? Menno. Menno, perfect.